So welcome to this pre-recording of lecture 31 of MCS 320, an introductory course to symbolic computation. In this part of the course we are solving equations. We solved polynomial equations, linear equations, and in this lecture we will solve differential equations. Now, differential equations on its own merits an entire course or even multiple courses. So we spent only one lecture on it within the context of symbolic computation. And there will be one running example that is the pendulum, for which we will see two mathematical models. The first model we will solve symbolically, and one type of symbolic solutions involve the Laplace transforms. In the second model, we will see damping. So we will add damping to the model, and that will then be solved mathematically after a rewrite of the second order model into a system of first order equations. So the purpose of this lecture is to illustrate the benefit of computer algebra systems such as SageMath to model the problem, to solve it, and to visualize. So here you see an animation running that was made with SageMath, but in an earlier lecture we have seen the tools how to make an animation. So I can give you some hint on how this animation is made. So the animation represents a mass hanging from a string, and we have one parameter that essentially controls everything that is the angle that equals the deviation from the equilibrium position. So this pendulum is in motion, and in this first model the motion goes on forever. When the pendulum is entirely still, would be entirely still, then it would be hanging with an angle equals to theta. So this angle of deviation is evolving in time, and the equation that describes this model is a second order differential equation with initial conditions. So we have at time equals 0, we have given the pendulum an initial deviation, no velocity, so the theta prime equals 0, and then we let the mass loose, and it started swinging back and forth. Okay, so how can we solve this? We can solve this with Laplace transforms. So Laplace transforms go from the time domain into the frequency domain. We can see this as a formal rewriting, which is quite appropriate in this symbolic computing class. So we have a little theta in function of t, and the Laplace transform is a big theta in s. So s is a new variable, and the Laplace transform involves the initial condition, so the initial displacement and the initial velocity. Now, what does one gain with this? Well, observe that the theta, the big theta in S, occurs linearly. So this has become a linear equation in the Laplace transform, and that's very straightforward to solve. We are mainly interested in the specific initial conditions, although we could leave those in as variables as well. So once we substitute the initial conditions, we obtain an explicit form of the solution as a function in time with the two parameters, so the gravitational constant and the length of the pendulum of the string at which the mass is attached, that length is still in there. Okay, so that is the symbolic solution. We can't leave it at that. We have to interpret this. By the way, going back to this animation, so everything is controlled by the position of this red dot, and the displacement is the sine of theta. So the x-axis, the x-coordinate is the sine of theta, and the vertical position is 1 minus cosine theta. So once you have that red disk moving, that essentially defines your animation. Then only you had to add the plots of the blue line. So here is another plot that we can make for a particular solution with these initial conditions, and then I pick for gravitational constant 10, and as in the animation, the length of the string is 1 as well. You see the red, the line in red is the trajectory of the displacement. In green, so the solid green curve is the velocity. So the velocity is negative because we go in the opposite direction towards the origin, in the opposite direction of the x-axis. So then when we cross the equilibrium position at deviation angle 0, then the velocity is actually decreasing. So here you see that the velocity is flat, the velocity is 0, and then it increases again. So what I'm trying to indicate is that you can interpret it this green line here. So we still go into the opposite direction until the green curve crosses the horizontal axis. So this is where the velocity vector essentially flips from positive to negative. So what you see in the slope field here, here we have one trajectory plotted, and you see that these arrows here very much line up. So the slope field indicates what you would obtain for trajectories for the velocity fields if you were to pick other initial conditions. Alright, that was our first model. In our second model, we're going to consider damping. So we have the same setup, but now our model is a little bit more general. So instead of the theta at the right hand side, we add the sine of theta. So adding the sine of theta, so for small angles such as pi over 10, you can see that the sine of theta is very much theta. The sine function in power series developments is an odd function. The next term is a cubic term. So the error term is actually quite small if the angle is also actually not very far from 0. Okay, so the point is that we include damping. You see that the animation slows down, and the damping is proportional to the velocity, inversely proportional to the velocity. So there is this gravitational force that works on it, but now there is also the friction. And with this constant a, we can determine how fast the pendulum dies out. So it's the same problem, a different model. And it turns out that for this model, it's already too difficult or there is no explicit expression for the solution. So then what we do is we compute a numerical trajectory of the displacement. Okay, so in order to do this, we have to rewrite the system of first order equations. We have to rewrite the second order differential equation into a system of two equations, but the two equations are of the first order. So this has some benefits. So I made a plot of the slope field with the velocity in there, while the numerical solver will actually compute both the displacement and also the velocity. So you can make the same plot as we did before based on the numerical output. So with this rewrite, we introduce a new variable, the derivative of theta. Then the second derivative of theta is the first derivative of the velocity. So we can replace here the left hand side, and we also replace the derivative that we find at the right side here by the velocity. So we have two equations with at the left the derivatives. So the L is 1 in our example, don't worry about the L, or we can divide. At the right sides we have only the original functions. So we have two equations of first order in two variables. The variables what we are solving for are functions in time. Okay, so that was the overview of the concepts of what we're going to do now with SageMath. So I'm going to flip to the Jupyter notebook, so flip away the slides. And I have a prepared Jupyter notebook. So to keep this a little bit dynamic, I will make a new notebook from scratch, and whenever I get stuck, I will copy and paste from my prepared notebook. So in this lecture we solve essentially the pendulum problem, once symbolically and once numerically. Okay, so let's look again at the pendulum problem. So the first step is to formulate the system that I'm going to use. So the independent variable is time, and I'm going to formulate the differential equation. When we considered implicit differentiation, we defined a function. So that this is what I'm going to do now as well. So the function will have theta as the string representation, and it will be a function in time. So then my ordinary differential equation is formulated with two parameters, the gravitational constant and the length of the string. And these two variables, they have to be positive. So I can add assumptions later, but I can also do this in one statement. So I can say the domain is positive. Without it, the symbolic solving won't really work. So now I can formulate the differential equation. So it's a second order differential equation. So the L comes to the right. And I have the minus gravitational constants times theta t. So, and the nicely typesetted equation comes over here. So then I'm going to solve this with the e-solve. So we've seen the solve in an earlier lecture. The e-solve is an also very important solver, but for differential equations. So I'm going to solve the ODE for theta, and I have to indicate that t is the independent variable. And you see this is a quite nice way of solving. Perhaps I should document now what I have done so far. We have a second order differential equation given without initial conditions. So the general solution is a family of two periodic functions with parameters, general parameters k1 and k2. So the k's kind of indicate that they are constants. So let's add the initial conditions. So I'm going to modify the statement. So I can provide the initial conditions. So at 0, I have that the initial angle is pi over 10 and there is no velocity. And then here I get the solution. So this is a solution that is symbolic. Perhaps I should also have neatly typesetted it. So here is the solution with two parameters, the gravitational constant and the length. So let me look at a particular solution now. A particular solution where I'm substituting the gravitational constant for 10 and the length for 1. So let me look at this problem. So this is a periodic solution, so I will plot p-sol, plot the particular solution between 0 and 2 times pi. Okay, so this is not so much to be so this is a plausible solution. The other thing that I want to indicate here is that pi over 10 was the initial angle, and if you look at pi over 10 and you also look at p-sol at 0, so that's the initial angle, and I probably should do this also for that actually fits the initial condition. So that's one check that one can make. Okay, how does one solve symbolically? So we can solve with Laplace transforms. And there is actually the e-solve option the fast way to do this would be to do the solve Laplace, where I'm not actually using that command that much. So let me copy and paste. And it is indeed what it is. It is just using the solve, but then with the underscore Laplace. Here we go. So what we see now is that we have the initial conditions sitting in there. So I did not provide the initial conditions. So we can substitute them in, and we've seen that dictionaries are very useful for substitutions. So what do I have? I have that theta 0 has to be replaced by pi over 10, and the derivative of theta at 0, that has to be replaced. So derivative of theta t with respect to t, and now I probably need to backtrack a little bit, because you see this notation. So I can say d theta is the derivative of theta with respect to time. But actually what I don't want the general function. I want the derivative of theta. So let me verify that that is really the d theta. So I want, and you see here this expression, I want a derivative of theta at 0. So how do I do this? D theta 0 is the d theta where I have substituted t for 0. And now you see that's actually what I want. So what I was trying to do here with the initial conditions, I was trying to type that in. So d theta, so the derivative of theta with respect to time, where you substitute time by 0. Doing all that all at once would certainly have ended in problems. So my two initial conditions are now stored in this dictionary. Why is that useful? Well, I have my solution, and now I can find the particular solution again, perhaps particular solution 2. I can substitute using the dictionary. And here you see that I have the same particular solution as I had before, except that I should still make it more particular. Actually, I have assigned. So the gravitational constant is 10 and L equals 1. So now you see that indeed they are the same. So this is the short way to use the Laplace transform, d solve Laplace, and you can most likely also give the initial conditions. Then you do not have to substitute in the solution. But also this is a form of symbolic solution. The advantage of this form is that you have the initial conditions sitting in there. So this is a form where instead of having the K1 and the K2, you actually now see the two families, the sines and the cosines, but you can also see what are these parameters in function of the initial displacement and the initial velocity. So solving with respect to the Laplace transform has already that benefit. Okay. let me do this now via the Laplace transform. So I'm going to introduce a new variable, s, and I'm going to do the Laplace transform of the ODE, where I'm going from t to s. If I remember correctly, then this should be the syntax. But the Laplace transform is not defined in the way that I thought it was. So it's simply Laplace. So it's a method that I can apply to the ODE, and the two parameters are the symbols, the symbol that I use for time, and the symbol then that I use for the new variable s. Okay, let me make this a little bit better. So I'm going to introduce a big T as a new variable. So that will be the big data. Perhaps I should, that might be confusing, but the big data with a capital T. And what I will do is in the ODE, I will substitute. So I will make this an equation in T. I will substitute the Laplace transform of theta t I will replace this by the big data. Here we go. So this clears things up. So this is the same calculation that I did on the slides. So actually I made the slides after I did this calculation. So you see that I have my big data sitting in there, and I can solve this equation with the regular solve. I can solve this equation for the big data. And that gives me the symbolic form of the solution in still the frequency domain, in the symbolic domain of the Laplace transform. So let me select this solution. So I probably have used solution a little bit too much. So I have to take the inverse Laplace transform of the right hand side. And note that the solution is a list, so I have to select the list. So that's the form for the TS, so call it TS. And let me nicely typeset it. So this is the form. And now I can compute the inverse Laplace transform. So that will give me then the general solution. So moving back to the time domain. And this gives me the general solution with the parameters sitting in there. So the two, well, I have the two parameters of the problem, the gravitational constant and the length of the string, but I also have the derivative and the initial, the first initial velocity, and then also the initial displacement sitting in there. So to check, so I have my general solution where I'm going to replace the gravitational constant by 10 and the L by 1. And I still have to substitute the initial condition. So let me do everything at once. I'm going to substitute the initial conditions, which are defined by this dictionary. And that gives me the same solution that we had before. So this is the same particular solution. Okay, that's a lot of formality, a lot of formal computations. So if you haven't ever seen this seems like magic. In a differential equation course, you work with lookup tables for the specific functions and to compute the inverse Laplace transforms and the Laplace transforms themselves. Here, SageMath knows everything necessary. Okay, before we transition to the numerical solving, let me look at one particular solution and let me plot the slope field. So the particular solution that I will be using is already p-sol. So I will plot this particular solution along with its derivative. So the derivative with respect to time will be plotted. So this is the, perhaps I should say that this is the velocity. So I will make a plot of the trajectory of theta and also make a plot for the velocity. So let me first do the velocity plot. For t from 0 to 2 times pi, and I will color this in green with some thickness, because I'm going to use this as a component in the slope field. So that's one plot. Let me extend this with the displacement plot, so the theta plot. So that's my particular solution for t, also ranging. And I will plot this in red, with also a given thickness, because I do want to add the slope field to this. So as I tried when I explained the slides, one can interpret the direction, one can see the direction of the red trajectory, if it's going up or down, which was left or right, and you can interpret this with the orientation. So if the velocity is negative, then we go down. If the velocity becomes positive, then we go up. So you see that the peaks of the green correspond to the zeros of the red. That's a nice interpretation. So let me now plot the slope field. I'm not doing this regularly, so let me copy the statement. So for the slope field, you need an expression in two variables. So the expression is actually the velocity. So I have to introduce a new variable, v. So I'm going to plot v minus the particular solution. So the particular solution is p-sol. And I have to execute this. And I will do the velocity plot plus the data plot plus the slopes, all in one figure window. The range should go from 0 to 2 pi. So here you see the slope plot, which illustrates what happens when you pick different initial conditions at different locations. Okay, so now I have about 15 minutes to introduce a numerical solver. So we've seen the general DE solve. There's also the eSolve that uses ODE int. But let me first say what we are going to do. We're going to consider the pendulum with damping. So the second order model, so let me simplify things a little bit. So the gravitational constant divided by L equals 10, and the damping factor is 1 over 1.2. So I pick numerical constants. So then the model is the following. So what is the differential equation? I still have the second derivative with respect to time of theta, which is compensated with this minus 1.2 times the velocity and I have the gravitational constant, so the L was actually 1, so 10 times the sine of theta t. So that's the model that we are looking at now, and I should correct things. So theta function of time, and I have to Greek letter theta. Okay, let's rewrite this now into a system. So to rewrite this into a system, we introduce velocity as follows. So the derivative with respect to time of the function theta is the velocity. And I can then rewrite the derivative with the second order derivative as the derivative of the velocity. And also put the velocity so now I have two equations, so if I'm typesetting them correctly. So at the left you see the first derivatives of the displacement and of the velocity, and at the right you see only the original functions, theta and the velocity. Okay, what do I need? So I have already the symbols theta. So we need to define now a right hand side. In the symbols v and theta. So I'm starting from scratch here. So I'm going to declare theta and v as symbols. So my right hand side is then expressed as v, and this minus 0.2 times v minus 10 times the sine of theta. So this is my right hand side. What I need is a range for time. So I have an end time. So let this be 2 times pi. I have a step 0.1, and then I have my time range, which is defined with this S range till the end time and with a step. Lastly, I have to define the initial conditions. So the initial conditions are 0, pi over 10. So now I need a number for pi, and 0. So these are the initial conditions. And now I can attempt to formulate the numerical solver. So it's the esolve ODE int. So ODE int is the SciPy package, or actually it's the ODE int of ODE pack. So that's another wrapper of a Fortran software. So that we're going to run now. So on the right hand side, on the time range, and with the initial conditions. So I hope that I did not miss anything. So yes, I did. So I had to specify that I'm solving this for theta and v. And now there is still something wrong. See if I can get this from... No, I made a syntax error. So let me look at my prepared. So I have my time range, my right hand side. That seems to be correct. Aha, I flipped the time range with the initial condition. That is my mistake. Okay, so now what I get from this is that I get the trajectories. So I get, perhaps I can ask for the dimensions of the solutions, or perhaps let me just look at it. So I have a two-dimensional array, and it's not that bad. So what you see is that the first column are the displacements, and the second column are the velocities. You can see this from the first entry, my pi over 10, and then my 0. So I will select all the rows from the first column, and I will make a plot out of this by just doing line. And apparently something went wrong, because I also must use the time range for something. So I must select. Um, so I have the angles that are coming in there. So now moving back for the angles, I must the points that I'm plotting. So I was too fast. So what I'm plotting is the time range. So I have the displacement angles that I select, and then I select the points. So I'm zipping. So for every the list of angles is as or the column of angles has the same size of the time range. So the time range, and I'm defining the angles here, and this is the zip, gives me a zip object, and I turn this into a list of tuples. Okay, and this then gives me the plot. So this is the plot of the displacement, and well, perhaps for extra credit, so let me also do the velocities. So where are the velocities? So the velocities are in the other column. So there I have my v points. So and then I will plot the velocities using the line on the v points and perhaps in another color. So I have then the plot sol plus the plot of the velocities. And if I didn't make any typos, and I didn't, then you see how this works. So the displacement angle dies out. The corresponding velocity also is damped out. Okay, so this was solving one example, one problem, the pendulum problem, with two different models, two entirely different techniques. So one technique is symbolic and gives us an explicit form. If there is no explicit expression for the solution, then we have to resort to numerical techniques, which gives us points that we can plot. Okay, I hope this was an interesting lecture. And I will stop now.